Top Secret. Psi Operative Training Mission. Reading passage. Light waves. Mission. Understand light and color. Use the PSYOPs team to understand the concepts to be better prepared for other missions. Tips. Remember to beam as you read through the passage below.
What happened to you last night? Weren't you supposed to be gathering intel on the Hive camp last night?
I was. It was just so dark out on our mission last night that I couldn't see my hand in front of my face because the batteries in my flashlight ran out. There was no light at all out there.
Correction, there was just no visible light.
Huh? That's what I just said.
There's an entire spectrum of light that we can't see with our own eyes. Human eyes are made in such a way that if there is no visible light, then there is no sight.
You're starting to sound a little crazy. What do you mean, visible light? I'm not blind. I can see light just fine.
Our eyes are limited and can only see certain wavelengths of electromagnetic energy.
I thought our eyes were supposed to help us see, so why can't we see the entire spectrum?
Visible light is just one very small portion of the electromagnetic spectrum. This spectrum is the entire range of electromagnetic radiation coming from the sun that is created by perpendicular electric and magnetic fields. The electromagnetic spectrum includes radio waves, microwaves, infrared waves, visible light, ultraviolet radiation, X-rays, and gamma rays.
You mean the energy used to make popcorn is made of the same type of energy my eyes used to see?
Yep, that's right. The only difference between the categories of electromagnetic radiation is the wavelength and the frequency at which the wave moves.
So there are some supersonic speedy waves and some super slow boring waves?
Not quite. All of the energy waves travel at a constant rate. You have probably heard it referred to as the speed of light, which is 300 million meters per second, or 3 × 10⁸ meters per second in a vacuum. However, some electromagnetic energy has a higher frequency and a shorter corresponding wavelength than others.
Don't we use frequency and wavelength to describe the laser waves?
We do! Wavelength is a measure of the distance between adjacent peaks, or troughs, of a wave, and frequency is the number of times a wave cycles in 1 second. In the electromagnetic spectrum, the categories don't have exact boundaries, so the ranges tend to overlap based on their behavior and uses.
So, light is just a small part of the electromagnetic spectrum.
Well, the word light can actually be used to describe the entire electromagnetic spectrum. But the words radiation, waves, rays, and energy can also be used. We tend to use visible light only to describe the wavelengths ranging from 380 to 700 nanometers, or nm, that our eyes can see.
Oh, I see. Or rather, I can see a small amount of visible light, but there's a large amount of non-visible light I can't see.
Exactly. Humans can only see a very small amount of the electromagnetic spectrum, but there are other organisms that can see a larger range. Our eyes act as receivers, or photoreceptors, to this energy and interpret it as white light. It wasn't until the 1660s that Sir Isaac Newton discovered that white light could be split into the colors of the rainbow.
How did Newton slice white light into the colors of the rainbow? Did he have a lightsaber or something?
I love the enthusiasm, but splitting light isn't like slicing light, and it's a lot simpler than that. Newton shined a beam of light through a prism, which bent the light as it passed through, splitting the white light into the 7 different colors of the rainbow.
Bending light sounds cool as heck.
Bending of light is called refraction, and each frequency of visible light wave bends at slightly different amounts. The shorter the wavelength and higher the frequency, the greater the bend.
If I'm understanding correctly, you're saying that different kinds of light bend or refract based on their frequency. Does that mean that each color of the rainbow is a different wavelength of visible light that has refracted and separated into its own frequency of light?
Exactly! If you look at the visible spectrum, the longest wavelength is red, and its corresponding frequency is the lowest. This means that it bends the least. The opposite is true of violet, which has the shortest wavelength and the highest frequency.
Finally, you're starting to make sense. It is easy to remember if you look at a rainbow and its shape. If you were to measure the red line, it would be the longest distance and it curves the least on the outside. Whereas if you measured the violet line, it would have the shortest length and would always be on the inside because it bends more.
Another thing that can help you remember is the mnemonic Roy G. Biv stands for red, orange, yellow, green, blue, indigo, and violet. You can see that red in the visible spectrum has a wavelength slightly shorter than the electromagnetic spectrum of infrared light, and violet is just barely longer than the electromagnetic spectrum category of ultraviolet light.
If we don't see the other categories of EM radiation, how do we see color when the light is not being refracted through a prism?
Well, sometimes we see light refracted naturally. When a rainbow is created, light bends as it passes through millions of raindrops and becomes a rainbow. Normally, we see color because of other wave behaviors like absorption and reflection. If a wave is not absorbed, where energy is taken into the object and converted into thermal energy, then it is reflected, or bounced back, into our eye. When the wave enters our eye, we see the color corresponding to that wavelength and frequency.
Got it. The hive look green because only green wavelengths of light are reflected back into my eye, and the other frequencies are all absorbed. But why does most sunlight look white instead of like a rainbow?
Well, when all the visible light energy is received together, our brain interprets that as white. Newton proved this by using a second prism to bend the light back together.
So if all the frequencies of energy are seen together as white light, then what is black?
Simple. When no energy is received by the cells in our eyes, our brains will see black. This is because no input has been received.
Okay, so it's like an on and off switch. When all energy is received, my eyes are on, and my brain interprets the energy as white. When no energy is received, my eyes are off, and I see black. Guess I'll need to find some way to make my eyes turn on so I can see better in the dark.
Or you could just remember to bring extra batteries for your flashlight next time.
Oh, right. I guess that would work too.
Make connections. In each box below, write a connection between the text that you just read and either your prior knowledge or something in your life. Reading comprehension questions. Electromagnetic spectrum. 1. What is the electromagnetic spectrum? 2. Select the words that can be used to describe the electromagnetic spectrum from the list below. Electricity, gravity, solar radiation, electromagnetic radiation, radioactivity, light, rays, nuclear energy, waves, energy, magnetic fields, solar energy, ocean waves. 3. What determines the different categories of the electromagnetic spectrum? 4. Circle the portion of the electromagnetic spectrum that humans can see. What wavelengths correspond to this range? 5. What behavior explains how a prism makes a rainbow? Why? A. Reflection, B. Refraction, C. Absorption, or D. Transmission? 6. Why are the hive green? A. Green frequency refracts into our eye, and all other wavelengths are absorbed by hive. B. Green frequency reflects into our eye, and all other wavelengths are absorbed by hive. C. Green frequency is absorbed by hive, and all other are reflected to our eye. D. Green frequency is refracted by hive, and all other wavelengths are absorbed by our eye. 7. How many colors of the rainbow are there, and what are they in order of wavelength from longest to shortest? 8. What is white light? A. Not a color. B. All the colors. C. A lack of color. Or D. The highest frequency wavelength in the visible spectrum. 9. Why is black not a color?